Cool. So in this video today, we're going to be talking about area of a triangle using the SAS method. Reminder that SAS stands for side, angle, side. And so an example of this might look like let's draw a triangle. We have our three sides. Maybe we are given this side right here, maybe give that a value of 12. And then we're also given this side, given a value of maybe 8. And then the thing with SAS is that the angle needs to be included. So included meaning that it is perfectly sandwiched between the sides given. So if I'm given these two sides, the angle needs to be included in here with no space in between. So if we're looking at that, maybe I added degrees of 54 degrees there. And so the first indication of how I might be able to use area of a triangle with the SAS method is having a triangle that is in SAS in terms of what I'm given. We'll show a couple other situations where you might just be given one side, and then we'll talk about how you'll go about getting the angle for that and the other side to recognize an SAS. But essentially, the formula to find area of a triangle using the SAS method is as follows below. So here's the formula. So the formula is always going to be side 1 times side 2 times sine, right? And that's a trig function. Theta, or the angle, the included angle in the SAS. All of this is going to be multiplied and then divided by 2. So this right here is your best friend when it comes to finding area of an SAS triangle. Now let's actually look at some examples of what a problem might look like, and we'll start first with just being given some triangles, the sides and angles included. So if we look at this, for example, we have a ton of triangles here. Maybe we'll look at the problem right here. And so what we have is we have a side, we have another side, and we have an angle. And it's the angle is included in between. So I can recognize this is an SAS. And I might be asked to find the area. And so we'll use the formula, side 1 times side 2 times sine theta all over 2. And so what this would look like using the values we have, it doesn't really matter which side is side 1 or side 2. It's in whatever order you want those to be in. So this would be 8 times 3 times sine 97. And so you'd multiply all three of these together in your calculator, then divide it all by 2, and then you'd get your area. And we won't go through the answers for all of those. I just want you to get used to setting up, using the formula and setting it up. But once you plug all those things in, it just depends what you're being asked for. For example, here we're being asked to round to the nearest 10th. You might be asked to round to the 1000th place or something different like that. So that's an example of that. Maybe we can talk about what it looks like on a right triangle. It's the same situation here. It looks like we have two sides and an included angle. Recognize that this is a 90-degree angle. So the setup would look like 3 times 3 times sine 90 all over 2. Plug that in and you'll get your area. But I want to look at a situation that's different, and this is more with regular polygons. And so we'll take a look at these examples here. And so now we're going to have to do a little bit more work. And so maybe we'll focus on this problem right here. So it asks us to determine the area of a regular heptagon that has a radius length of 12 centimeters. And so you need to remember how to be able to draw a radius on a regular polygon. In this case, it looks like we have a heptagon. So I'm going to go ahead and go over here. I'm going to underline this information because it's important. And I'll take this point in the middle here, and then remember that you are not going to be drawing from the center down to the middle of a side. If you do that, that is your apothem, or the height of a mini right triangle. When you want to draw a radius on anything, it's always going to be from the center to a vertices of the polygon. So these are all the vertices, so let's go ahead and draw this to this vertex here. So that's connected, and that's going to represent my radius. And so they're telling me that this has a value of 12 centimeters. And then here's what's nice. We know that regular polygons have equal sides, have equal angles. What you must remember about circles, isn't the best circle, but the distance from the center to the edge of the circle is the radius, right? But we can draw that anywhere we want, and the value of our radius is the same anywhere we go. And so what we could do is we could completely finish drawing this out into a mini triangle, and I can draw from the center to this vertices another radius, and I would know that the value of that would also be 12 centimeters, because like I just said, the value of the radius is always going to be the same. And so as you can see, we've been talking about SAS. I have my two S's, but the last thing that's missing here is my included angle. And so remember to find this angle right here. This is called your central angle. And to find your central angle, you're going to take 360 and divide it by the number of sides. And so we have a heptagon. The heptagon has 7 sides, so we're going to take 360 and divide it by 7. And so our value there is going to be around, I'm going to just round it to maybe, let's just call it like 51 degrees. And now I have an SAS, right? So what I did was 360 divided by 7 because of those 7 sides. And then I can finally find my area using the formula from before. So here's my SAS, side 1 times side 2. So you're going to set up 12 times 12 times the sine of 51 degrees. And it just depends, you know, what kind of degree measurement you're going to use and how you rounded it. All divided by 2. And then find the area, round it to whatever it is. I want to see if there's another problem we could probably look at. Here's a good one as well. So this one has no visual, for example. And so find the area of regular dodecagon, has 12 sides, the radius is 32. So instead of having to go through the trouble of drawing an entire 12-sided polygon, I can just focus on drawing one of those mini triangles from the inside. So I'll try my best to draw that just like this. And I'm going to know that this is the center, and then this here and this here, those are the vertices from this dodecagon. I know that my radius has a value of 32. And so this would be 32, and this would be 32. And so the last thing I need to do is figure out what that included angle is going to be. So I'm going to take, it's the same thing as your central angle. So you're going to take 360 and you're going to divide it by the 12 sides. And so that included angle, so 360 divided by the 12 sides is going to give us 30 degrees. And so right in here, we have that. So now I have SAS, and I can set up my area formula, which is side 1 times side 2 times sine 30, all divided by 2. And then you'll get your area right there. All right, I hope this was helpful. There's a lot of different ways in which you're going to see this. Even this last one right here, for example, right, you might be given a triangle. Recognize that these lines mean congruent marks, so they're already telling you that this side's also 15. And set up that same formula, side 1 times side 2 times the sine of your included angle. I hope that was helpful. Please let me know if you need any more examples with this kind of work.